here we go with 2.2. You might be happy to hear that in 2.2 we're changing gears a little bit, like we're not doing the exact same thing as from 2.1. 2.1 was about verifying identities. There might be a little bit of that as we go forward in the unit, but I mean, we are, at least to a large extent, changing gears. And what we're doing now is we're going to be kind of going through that formula sheet. And because there's all kinds of cool things that, years and years ago, mathematicians sort of found were true and proved were true with these trig functions. And we're going to see how they can be used and how we can work with those and what kinds of things we can do. So section 2.2 is about the sum and difference formulas. So if you look on the formula sheet that should be in your possession, I think after I just kind of have all those basic identities again, like the reciprocal identities and stuff. So maybe towards the bottom of the front side of that handout, we got the sum and difference formulas. Again, these are just truths that at some point somebody or a group of somebodies work together or work to discover and prove were true. And just as one example here, if you have the sine of a sum of two separate angles, like x and y we're going to call them, that is actually going to be equal to the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. So, and I guess throughout the rest of the unit, x and y can be known as different things, like maybe a theta can be thrown in there, or some other Greek letters that we use as variables. I'm talking about, what I'm thinking of is alpha and beta, So, I mean, don't ever get mixed up by like what the variables are, but on your sheet, it looks like we're using a lot of x and a lot of y, at least here. So that's why they're called the sum and difference formulas, because it's the sine of a sum of two angles, cosine of a sum, tangent of a sum, and it's always equal to this other side. And over here, this is like the sine of a difference of two angles. And let's see how we can use this stuff. So, example 1, we want to find the, let me get my pen, find the exact value of the sine of 15 degrees. Because you could go on your calculator and, with our, these days in 2018, we have these yellow calculators. You might know what I'm talking about. I wonder, this is like, talk about doing this live. The sine of 15, that's pretty neat. It looks like what I just did is I did do the sine of 15 on these calculators, and I guess if you have the right calculator, like the yellow one, that's in the right mode, math print, I guess in this case, on the yellow calculators, I guess the calculator will give you an exact answer. So, so I guess for some full context, a lot of calculators, or I guess if you changed modes on this yellow calculator, other kinds of answers a calculator would give you would be like in just a decimal. So you could get a decimal answer from a calculator, but that's not what I call exact. So it looks like, at least in 2018 and in the foreseeable future, it looks like you're going to need to show some work on quizzes and tests in order to just make me sure that you didn't just do this on a calculator, that you know what the sum and difference formulas are all about. So anyway, sorry, let's get back to it. So here's what we're going to do. The sine of 15 degrees, as far as last unit, not one of the special list of angles that you can do with SOHCAHTOA and a triangle or with unit circle coordinates. 15 degrees just wasn't on that list. Just, you know, it was more like 30, 45, 60, 180, 150, 225, 315, 330. You know, 15 degrees was on the list. So we're going to utilize one of these formulas, and well, I mean, I think we can narrow it down to like either this one or this one. We're going to use one of those two formulas to get the job done. Okay? And, well, think about that. How can we utilize the sine of a sum of two angles or the sine of a difference of two angles and what they equal in those formulas? How can we utilize one of those formulas in order to work with the sine of 15 degrees? Well, I guess that's not too... Probably should have moved this box first over here. What if we rewrote 15 degrees as 45 degrees minus 30 degrees? You know, because 45 degrees was one of our go-to or special angles that we can do without leaning on a calculator. And same with 30 degrees. So if we can rewrite an angle using two of our nice angles, that would get us going. So we can pretty much treat the 45 degrees as the x, or angle number one, and we can think of the 30 degrees as the y, or angle number two. And once you rewrite this as like this, you could rewrite it as this, because that's what the formula says, that it says this is equivalent to this. So I can kind of change it to this other side. And I mean, we just said x was 45 degrees and our y we're calling 30 degrees, and so we get to here. Okay, like now we're really making some progress, aren't we? Because the sine of 45 degrees, we can do that without quote-unquote cheating on a calculator. And we can do the cosine of 30, and we can do the cosine of 45, and we can do the sine of 30. Now, here's where I tell you or remind you of the very good news that last unit you would have had to like draw a triangle for this, draw a triangle, draw a triangle, draw a triangle. So in a way, this is like 4 problems at once. But that's why I gave you the other handout for the unit, which pretty much like you can look at the, I guess you could call it a table, where you can just look at the reference sheet and see, oh, the sine of 45 is this. Oh, the cosine of 30 is this. Save some time, you know. I don't think you should forget how to do the sine of 45 or the cosine of 45 or the sine of 30, you know, without cheating on a calculator or by looking at a reference sheet. But for right now, I don't want you to take an hour on these problems, so we can just kind of look at our paper and get to this part. Okay, so what happens next? Well, right now it'd be just a matter of simplifying, right? Cleaning things up for a final answer, you know. So it looks like we should multiply those fractions together, multiply those fractions together. Do we need common denominators to multiply fractions? No, we don't. So we just multiply the numerators together, we multiply the denominators together. You know, we multiply across, as some people say. And root 2 times root 3 is root 6. 2 times 4. Root 2, root 4. And can we do that subtraction? Actually, yes, and very easily. We can do it without any extra work because they already have the same denominator. And that's what you need in order to subtract fractions. Now, what's root 6 minus root 2? Well, we can't really do that. We can't combine those together. So that is actually our final answer, right there in blue. Root 6 minus root 2 all over 4. And that is, I guess I got to retype this into my calc. That's exactly what the calculator told me, since it was in the right mode and everything. Okay, example 2. Find the exact value of the cosine of 40, cosine of 20, minus sine 40, sine 20. This is actually similar but different. That tells you a lot. This is similar but different to example 1. I guess through practice and study and whatever and an effort, you just have to start to see this and recognize it as, what was this again? Cosine, cosine, minus sine, sine. Cosine, cosine. Minus sine, sine. See, let me say this right now. You will have this formula sheet available on the overall Unit 2 exam. Okay, the 100-point test. So what I'm saying is you don't have to memorize all of these formulas because you'll have this paper. A new copy of it, on the day of the test. But so you won't have to memorize all of these formulas, but you do have to be familiar with them. You do have to sort of know what's there and how to use them and how to apply them. I guess what I'm really saying is you should see this and maybe not know exactly which formula this is referring to, but you should be like cosine, cosine, minus sine, sine. That seems awfully familiar. And then you can look at your paper and go, oh, it's this. And what all of this equals is basically this, the cosine of a sum. So here it's like 40 is our first angle and 20 is our second angle, like our x and y. And so you can just, well, that's okay. I wasn't expecting that. I don't even think you need to actually write that out, but or maybe even that. But that's what's going on. Ultimately, okay, let's. Ultimately, whether you need to write this down and this down or not, this cosine 40, cosine 20 minus sine 40, sine 20 gets changed into just that. The cosine of the sum of these two angles. And, I mean, what's 40 plus 20? 60. And so this really, all of this just boils down to this, which is 1/2 according to your reference sheet. Your cheat chart. What is the cosine of 60? And it's 1/2. So that's example 2. So you'll need to do examples where you kind of change you take something that is comparable to the left side of one of the formulas and change it to the right side. There will also be examples where you take what's given to you as comparable to a right side of a formula and just change it back into the left side. to make things doable and to get to like a final answer. Example number 3, verify the identity. Verify. So we're back basically to section 1, the section you loved with all your heart. And but verify the identity, same thing as what we did last section, okay? But now it looks like we're just going to be throwing in stuff like this. The cosine of this, alpha, this is called alpha, minus beta. It's just 2 other Greek letters that we can use as variables. Could this have said x minus y, and so there would be x, that would be y, that would have been x, that would have been y. It doesn't make a difference, just different variables. You've been doing this ever since 7th grade or so, Doesn't matter what the variable is. Anyway, so where was I? So, again, just like last section, we're going to want to rewrite the left side and or rewrite the right side until they literally say the same thing. So what are we going to do first? Well, look, I think this should be even a little obvious at first. We need to rewrite that. Like we just learned what that is equal to, and so I think that's what we're going to do. We're going to look at our formula sheet and see that the cosine of a difference, which is right here, let's get rid of this now, but the cosine of a difference is equal to all of that. Cosine, cosine, plus sine, sine. And so that's why I wrote this. But instead of x and y, it's alpha and beta. Okay, get over it. And the bottom just kind of stays. How about over here? Should we rewrite the right side? We didn't really like, for the most part, having cotangent involved when we could just change it to cosine over sine. This is alpha only. The cotangent of alpha is the cosine of alpha over the sine of alpha. And the tangent of beta is going to be the sine of beta plus the cosine of beta. So we like to change everything to sine and cosine stuff. And what can we do next? What can we do next? How can we rewrite the... Well, listen to this. I don't know what I ended up emphasizing in class. I probably emphasized both options, but what I did here was I worked with the left side, even though you're probably more likely, based on what we did and what I said, everything I said, you're probably more likely to look at the right side and say to yourself, I can add these fractions together as long as I make common denominators. As long as I rewrite each fraction so that they have the same denominator. So that's what you totally could do. Work on the right side in order to add these 2 fractions together. But what I did here was just break this fraction up into 2 fractions, each with this denominator, and just like that, the left side and the right side perfectly matched, and I was done. But, so I guess this was less work, like hindsight being 20/20. This probably was the easier or less arduous way to go about it. But again, you could have, worked on the right side and added them together, and then trust me, when you would have added these fractions together, it would have been that, and you would have been done in the same fashion. But here we go. Example number 4. Find the exact value of the sine of 7 pi over 12. Well, and they also say this, using the fact that 7 pi over 12 is the same as this sum. Interesting. So it looks like 7 pi over 12 was not so nice of an answer. Like if I would have said, what's the sine of 105 degrees? Like if I would have said that to you last unit, you would have had to grab a calculator. But, you know, now, especially since they told you this for free, you know, now that we know that it's the sum of, ooh, that's a nice 68 degrees, that's a nice 45 degrees, we can rewrite 7 pi over 12 as that. And if you want to, like, just go with degrees here all the way, that's fine. You could write this as the sine of 60 plus 45. I don't care. But, so this is just sort of helping you rewrite this as the sum of pi over 3 and pi over 4. Angles we really, really, really like. And at this point, they're angles that are on our cheat chart. So what do I do next? Now that I have it written as the sine of a sum, you can rewrite it using your formula sheet as this. And once again, even you might actually be writing it out like this now, but this is really the sine of 60, cosine of 45, cosine of 60 degrees, sine of 45 degrees. Go to your cheat chart, and those are all the answers. And now all you got to do is simplify that up for a final answer. So this was just like example 1, wasn't it? All right, example 5. Here we go. Suppose that the sine of alpha is 12/13 for a quadrant 2 angle. So alpha is a quadrant 2 angle, and the sine of beta is 3/5 for a quadrant 1 angle beta. Find the exact value of each of the following. Okay, so the first thing we want to do is figure out what the cosine of alpha is. So alpha, well, we know the sine of alpha is that, and alpha's in quadrant 2. This is a callback to last unit. We did this same exact thing. Last unit, they give you sine, the answer for sine. They give you information, or maybe they just flat out tell you, what quadrant you're in, and you have to find, the cosine of whatever, or x, or the tangent, or whatever. So this is what we did last unit, people. Based on the sine being 12/13, that's y and that's r, what else do we need? What else do we need to figure out the cosine of alpha? We need x. So we do the Pythagorean theorem. We end up taking the square root of both sides to get plus or minus 5, but it's not both of them. It's either positive 5 or negative 5. That's where this comes into play. If we're in quadrant 2, x is negative 5. Okay? What's this? Because of quadrant 2? Yeah. Quadrant 2. So x is negative, and so now that we know that x is negative 5, cosine is negative 5/13. Okay? So now that's the cosine of alpha. Next, over here to the right, we have to do the cosine of beta. Same thing. We know the sine is 3/5. We do the Pythagorean theorem. ... When we find x, is it going to need to be positive or negative? We're in quadrant 1. So positive 4, because we're in quadrant 1. And so therefore, the cosine of beta is positive 4 over 5, 4/5. Now we want to do the cosine. Okay, this is where, I mean, look at this. Cosine of a sum. You know, it looks like we're going to be using the formula. So it looks like we're going to rewrite it based on what it equals in the formula. Cosine alpha, cosine beta, minus sine alpha, sine beta. That's directly from the formula sheet. And I want you to remember, if it didn't already occur to you, we know this. We know that. We figured these guys out like a minute ago or less. And these were told to us in the first place. So just kind of replace those with what they equal. And same as earlier examples, we just kind of multiply the fractions together, those two fractions, and those two fractions. And we do negative 20/65 minus 36/65, and we get that. And, oh, well, I mean, this is the same kind of deal. In order to do the sine of alpha plus, remember, you can always pause the video. I know I'm probably flipping through these pages a little too fast if you're actually trying to copy everything down. You can pause. But the example D, very much the same kind of deal. We want to take the sine of this sum and rewrite it as what it's equal to in the formula, on the formula sheet. And we know all of these at this point in the problem. And nothing new to say. Same old stuff. Example 6. Oh. Tangent, finally. Find the exact value of the expression, the tangent of 300 minus 45. Interesting that they didn't just say the tangent of 255. I mean, because it isn't 300 minus 45, isn't that 255? So why didn't they just present it as the tangent of 255? I'll tell you why. They're trying to help you. You know, they could have given it to you as the tangent of 255. You would have had to come up with something like this on your own then. Because 255, not one of our nice angles, you know, as far as last unit goes. But 345, those are nice. Those were like, we worked with those. So basically, it's almost a good thing that they gave you the original problem looking like this, because now it's the tangent of a difference. We have a formula for that. So you go to your, it looks like our x is going to be 300 degrees and our y is going to be 45 degrees. And we find this on your formula sheet right here. The tangent of a difference is equal to that. So basically now all we do is, well, x was 300, y was 45, bam. So it becomes that. And why does this get us places? Because we know what the tangent of 300 is exactly. We know what the tangent of 45 is exactly. We can just go on our cheat chart. So the tangent of 300 is negative root 3. The tangent of 45 is 1, and so we get, to here. Now, what is there to do from here? Like looking at this and sort of regrouping, taking a breath, what happens now? Well, we should probably just multiply those together, for crying out loud. we get this. Okay? Now, even though you obviously see more box in here, we could totally be done right now, okay? This is, I mean, that's an answer. But I think what's about to happen here is, oops. I don't know if you need to write this down. I mean, maybe you should. I mean, why the heck not? But if you were to actually go through the motions of rationalizing this crazy denominator, and this is what you'd have to do in order to rationalize this denominator. It was like one of those extra tricky, examples of rationalizing a denominator when it's like a couple of terms here. You'd end up with this. So this, here's the thing, I bet this is what our fancy calculators would say is like the final answer for, if all you really plugged in was this, or just plugged in the tangent of 255 degrees, I bet your calculator would just say this. So this is a good final answer, but I mean, this is, again, you can't just have this, you have to show work. But you could have this or this. Now here's what I think I really want to emphasize. Not so much the green work, but here's what I want to emphasize way more than that. If this had just said 255, it didn't, but if it just said 255, 300 minus 45 is not the only pair of nice angles. I mean, I'm saying this, I hope I'm not wrong about this, because this is usually, if not always, correct. 300 minus 45 is not the only way to get 255. 255, let's see here. So couldn't you also do 225 plus 30? Isn't 225 and 30, aren't they both nice? So anyway, just my point is, if you were to write 255 using a couple other nice angles, you might get something different than what's here in red. So there's plenty of correct answers. Well, not plenty, but normally there's at least one or two correct final answers like this, and maybe even something else, which is acceptable as a final correct answer. And I guess that just like that was actually kind of a long video, I bet, but just like that, it's 2.2. That's it.